Hello everyone, welcome to this lecture. The plan for this lecture is as follows. So in this lecture we will introduce the definition of matching, we will discuss about complete matching, and we will see the theorem statement for Hall's marriage theorem. So let us begin with bipartite graphs and matching. So just to recap, in the last lecture we discussed what are bipartite graphs. They are the graphs where the vertex set can be partitioned into two disjoint subsets V1 and V2, with each of the where for each edge in the graph, one of the endpoints is in the vertex is into the subset V1 and the other endpoint is in the subset V2. Okay, and it turns out that bipartite graphs are very important class of graphs used to model various real-world problems, and one of the problems for which they are used extensively is that of job assignment. So let me demonstrate the job assignment problem with this example. Imagine you have two organizations, organization 1 and organization 2. Both of them are trying to build a software, and say the software has four modules. It has a requirement module, architecture module, implementation module, and testing module. Okay, and say both organizations have their respective employees. So organization 1 has employees A, B, C, and D. Each of these employees can handle one of the four modules required in the software. And uh, the skill set of each employee is modeled by adding an edge between the node representing that employee and the node representing the corresponding skill set which that employee can handle. So for instance, this edge here denotes that the employee A is capable of handling requirement, and this edge from A to testing denotes that he is capable of handling the testing module as well. In the same way, the employee B can handle three of the modules. It can handle architecture, it can handle implementation, and it can handle testing and so on. Similarly, the edges are added in this graph representing the skill set of the employees in the organization number 2. Okay. Now the job assignment problem is the following. Since we have to build a software, we have to ensure that each of the four modules, namely requirement, architecture, implementation, and testing, are taken care. So we want to assign employees to do the jobs as per their skill set, such that each job is attended by some employee. But at the same time, we do not want to be very strict or unfair with an employee by assigning multiple jobs as per its skill set. So for instance, I do not want to do the following. I take the employee B and assign architecture, implementation, and testing, all the three, to the employee B. That I do not want to do. So I want to assign each employee at most one job. When I say at most one job, that means it's fine if I don't assign any job in my job assignment, or when I'm assigning job to the employees to a particular employee. It's fine. I just want to ensure that each job goes unattended, and at the same time I do not assign multiple jobs to any employee when I am doing the job assignment. So that's my job assignment problem. So it's easy to see that of the possible job one of the possible job assignments in organization 1 is the following. I I ask employee D to take care of the only job that it is capable of doing, namely requirement. And then I take the employee B. So employee B can handle architecture, implementation, and testing. So I choose architecture for employee B. I pick employee C and assign the implementation module to employee C. And then I take the employee A and assign the testing module to the employee A. So that's possible. So I can come up with one job assignment in the organization 1 satisfying this criteria. But if you take the second organization, it's not at all possible to come up with a job assignment in organization 2 satisfying these conditions. Why so? So let us try to come up with one possible job assignment, and then we will see that we will get stuck here. So for instance, let us start with W. and W is capable of only handling architecture, so I can say W and architecture. W is assigned architecture, so we have taken care of W and architecture. Then we go to X. X can handle requirement, implementation, and testing. So let's assign the requirement module to employee X. Now let us go to employee number Y. Employee number Y can only handle architecture, but I have already assigned the architecture module, so no need to again assign it to any other employee. So I can say, okay, let Y go, uh, let us not assign any job to employee Y. And then if I go to employee Z, he can handle architecture, he can assign, he can handle requirement, architecture, and testing. Requirement and architecture are already taken care. Then I can assign only testing to employee Z. But in this whole process, in this scheduling, the module implementation is not assigned to any employee. It goes unattended. Okay. And you can try other possible combinations as well. You will see that irrespective of the way you try to assign the jobs, you can't come up with a job assignment satisfying these conditions. You can't do that in this graph. So whatever we have discussed in this example can be modeled by a concept called matching. So imagine you are given a simple undirected graph. Okay, that's important. Then a collection of edges denoted by M is called a matching if no two edges in this collection of edges M are incident with the same vertex. Formally, what I am saying here is the following. You take any pair of edges EI and EJ belonging to the collection of edges that you have picked. If they are different, then all the four endpoints, the two endpoints of EI and the two endpoints of EJ, they should be distinct, they should be different. I stress here, this condition EI not equal to EJ is important here in this implication, because if I take the same edge EI and the same, if I take the edge EI and EJ to be same, of course, the first one of the endpoints of EI will be same as one of the endpoints of EJ and so on, right? So this inequality won't hold if my EI and EJ are same. So this condition, this implication should hold for every pair of distinct edges EI and EJ from my collection of edges that I have picked. I stress here that there is no restriction on the cardinality of M. I can just pick one single edge from my edge set that will constitute a matching. Or I can pick two edges from my edge set, and if they satisfy this implication, that will also be considered as a matching and so on. Okay. So what this implication mean on a high level is the following. If I take the vertices of all distinct edges in my collection of edges M, they should be distinct. Okay. So again, if I take the job assignment problem and organization number one, what I actually did there was I picked the matching. Okay. My matching was this collection of edges. Namely, I took the edge D, requirement, B, architecture, C, implementation, and A, testing. And you can check here that you pick any EI and EJ which are distinct in this collection of edges M. There, the four endpoints will be distinct. Okay. So if I have a matching M, then a vertex V in my graph will be called matched with respect to that matching if the vertex V is the endpoint of some edge in my matching. Otherwise, the vertex V is called unmatched. So formally, this means that there should exist some edge small e and some vertex u such that the edge u comma v is there in my graph, and that edge is nothing but the edge e. If that is the case, then I will say that the vertex v is matched. In fact, the vertex u is also matched with respect to the matching if I have an edge of the form u comma v. Okay, in my if I have an edge of the form u comma v in my collection of edges m that I have picked. Okay, So, so for instance, if I take this graph here, and if this is my matching M, then I have vertex number A matched because there is an edge with one of its endpoint being A. I also have vertex B matched with respect to M because I have an edge with B as its endpoint and so on. Okay. Now we have different types of matching. So we have what we call as maximum matching, and it is a matching which has the largest cardinality. That means it is the collection of edges whose cardinality is the largest. That means you can't have a matching whose cardinality is bigger than the collection of edges or the matching that you have picked. So if I take this graph, then the maximum matching here is the collection of edges AB and CD. Okay, its cardinality is 2. Whereas if I take the matching M prime equal to B comma C, then that's not a maximum matching. Why it is not a maximum matching? Because the cardinality of M prime is 1. By the way, the matching M prime is this collection M prime is indeed a matching because um, the endpoints are distinct here. You don't have, first of all, the second edge here. So if you just take any edge, by default, it's a matching, right? So this is a matching, M prime is a matching, and it's not a maximum matching because you have only one edge in M prime, whereas you can have another matching M which has two edges in it. So M prime is not a maximum matching here. However, the matching M prime is maximal matching. So there is a difference between maximal matching and maximum matching. So what is a maximal matching? A maximal matching is a matching which cannot be further extended. And what do I mean by cannot be further extended? By that I mean that you can't find another matching M prime such that M prime is a superset of your matching M. Because if you can find another matching M prime, which is a superset of M, that is equivalent to saying that you can extend. That means you can add further edges in M and still get a matching of bigger cardinality. Right? That's what is the interpretation of cannot be further extended in this definition. Okay, so that's why your matching M prime is a maximal matching because you can't add any other edge now in M prime and still get a new matching. Why so? Because I can't add the edge a comma b in M prime because if I add the edge a comma b, right, to get say M prime, then M prime is not a matching. M double prime is not a matching because in M double prime you will have the edges AB as well as BC, and you don't have all the endpoints of any pair of distinct edges distinct. So here you have the edges E1, E2 such that one of the endpoints of edge E1 is same as one of the endpoints of the edge E2, right? Which goes against the definition of matching. So that's why M prime here in this example cannot be further extended and hence it's a maximal matching. Okay. In the same, whereas if I take the matching C comma D in this graph, okay, it is not maximal. Why it is not maximal? Because I can further extend my matching M and get a bigger matching. Namely, I can add the edge A comma B in this matching and it will still constitute a bigger matching here. Okay, so that's why there are two types of matching here, maximum matching and maximal matching. Of course, every maximum matching is a maximal matching. Okay, but other way around need not be true. You may have a matching which is just maximal, but it is not maximum. And one example is this. The matching C comma D is maximal. The matching, sorry, one example here is this B comma C, the matching B comma C. It is a maximal matching, but it is not maximum matching. Okay. Now we have another kind of matching called as complete matching. And what is a complete matching? So imagine you are given a bipartite graph with bipartition V1 comma V2. Then A matching in this graph is a complete matching from V1 to V2. And when I define a complete matching, it is very important whether the complete matching is from V1 to V2 or from V2 to V1. They will be different in general. So here I am giving the definition of a complete matching from V1 to V2. So the matching M that I have picked is called a complete matching from V1 to V2 if every vertex in V1 is matched with respect to my matching M. Or equivalently, the cardinality of the vertex set V1 should be exactly the same as the cardinality of your matching. This is because if every vertex in V1 is matched, right, that means I have edges in my matching M where for every vertex small v in V1, there is a corresponding edge with V as its endpoint in my matching M. And as per the definition of a matching, I can't have any other edge as well present with the same endpoint V. That's not possible. If I already have an edge with V as its endpoint in my matching M, I can't include any other edge in my matching M different from this edge which has V as its endpoint. That automatically means that the number of edges in my matching M that I have picked should be exactly same as the number of vertices in my subset V1. If that is possible, if that is the property of my matching, then I will say that my matching M is a complete matching from V1 to V2. Whereas if I want to find a complete matching from V2 to V1, then then the matching should be such that its cardinality should be exactly equal to the cardinality of uh, V2. Namely, it should be ensured that every vertex in V2 is matched, and that's possible only if the cardinality of M is same as the cardinality of V2. Okay. So for instance, if I take this bipartite graph, and it's easy to see that this is a bipartite graph because I can put A, B, C, D in one subset, and I can put uh, requirement, architecture, implementation, and testing in another uh, subset. And this is a bipartite graph, but it is not a complete bipartite graph. And when I'm defining complete matching, I don't need a complete bipartite graph. It is defined with just bipartite graph. Why this graph is not a complete bipartite graph? You have many missing edges here. So for instance, I don't have the edge from D to testing and so on. This edge is not there. Okay. So if this is my V1 and V2, and if I pick this matching M, then it constitutes a complete matching from V1 to V2. Why it constitutes a complete matching from V1 to V2? Because all the vertices in V1 A are matched. A is matched, B is matched, C is matched, and D is matched. In fact, in this particular example, this matching is also a complete matching from V2 to V1 as well, because I can interpret this matching as if it covers each and every vertex in the vertex set V2. So requirement is covered or matched, architecture is matched, the node implementation is matched, and the node testing is also matched. Okay, so now let's talk about um, a necessary and sufficient condition for checking whether there exists complete matching in my given bipartite graph or not, right? So if I am given a bipartite graph and if I want to check whether there exists a complete matching from V1 to V2 or a complete matching from V2 to V1, there should be some procedure for doing that. Can I say that there exists some graph theoretic properties by checking which I can declare whether the given graph has a complete matching or not? And there exists a very simple condition. That condition is also called as Hall's marriage problem. If you are wondering why the term marriage is coming here, because the condition is given in the context of a bipartite graph where the vertex set V1 and V2 corresponds to the set of boys and the set of girls, and the edges basically in the graph represents the preferences that the boys have for the girls. So if some boys prefer some girls, and vice versa. You will have the corresponding edges between the vertex sets in V1 and V2, and we would like to find out a complete matching from V1 to V2 in the sense that we would like to ensure that each boy gets a wife or a bride with respect to the preferences that he has, and we want to ensure that all the boys are covered. Okay, so that's equivalent to saying that I want to find out a complete matching from the set V1 to V2. Okay, so Hall gave the necessary and sufficient condition for that problem, and that necessary and sufficient condition is also called as the Hall's marriage condition. Okay, so I have given here two graphs. So this is my graph number G1 and this is my graph number G2. Okay, the interpretations of V1 and V2 are different in G1 and G2. In G1, the vertex set V1 are my employee set, and the vertex set V2 are the skill set. Where in my graph G2, I have made the skill set as the vertex set V1 and the employee set as the vertex set V2. Okay, so you can see that uh, in the graph G1, I have a complete matching from V1 to V2. That means I can ensure that all the nodes in V1, namely A, B, C, and D, are matched with respect to the matching that I have formed here. Whereas if I take the graph G2, then I can't have a complete matching from V1 to V2, right? Now, why it is not possible to have a complete matching from V1 to V2? And we already saw when we discussed the job assignment problem that in this specific graph G2, it's not possible to do the job assignment. So recall the job assignment problem was that we want to ensure that each of the four modules, namely requirement, architecture, implementation, and testing, are taken care by some employee. But at the same time, I do not want to assign uh, more than one job to any assignment, to any employee. That problem can be modeled as if you want to find out a complete matching from V1 to V2. Because if you want to find a complete matching from V1 to V2, that is interpreted as if you want to pick a subset of edges in G2 such that no two distinct edges in that subset has a common endpoint. That is equivalent to saying that there exists no employee who is assigned multiple jobs, and at the same time you want to take care of all the four modules. So that's why complete matching from V1 to V2. I don't want to cover all the employees. It's fine if some employee is not assigned any job. My goal is to assign or ensure that each job is taken care, right? So that's why the complete matching is from V1 to V2. And it turns out that in graph G2, there is no complete matching from V1 to V2. So if you are wondering that why a complete matching is possible in graph G1, but why a complete matching is not possible in G2, what exactly is the difference? What exactly is the source of problem in graph G2? Well, the source of the problem in the graph G2 is this specific subportion of the graph. If you take this specific subportion of the graph, then we have we have three modules, namely the requirement module, implementation module, and testing module. And there are only two employees who can take care of these three modules, right? So in terms of graph theoretic properties, I have a subset V1 dash here and a subset V2 dash here, such that the number of neighbors of V1 prime is less than the number of nodes, so such that the number of neighbors of V1 prime is less than the number of nodes that you have in V1 prime. Okay, so the number of neighbors altogether is 2, but you have 3 nodes in V1 prime. So how can it be possible that you take care of requirement as well as implementation as well as testing and at the same time ensure that neither the employee X nor the employee Z is assigned more than one job? That's not possible, because if at all requirement is to be taken care, it can be taken care only by either the employee X or by the employee Z. Once you assign it to employee X, say for example, then you can't assign employee X any other job. So you will be now left with two more modules to be taken care, but now you have only one employee left. Okay, how can that be possible? You will be able to only assign testing to employee Z, and now the module implementation will go unattended. Right, so that's the source of problem in graph G2, which is not allowing you to find out the complete matching from V1 to V2, and that's precisely is the formal statement on the necessary and sufficient condition given by the Hall's-Marriage theorem. So to understand the necessary and sufficient condition given by the Hall's-Marriage theorem, let us first introduce a few definitions here and notations. So if I have a graph G, then the neighbors of a vertex V, small v, is denoted by this notation n of v. And what exactly is the neighbor set of the vertex V? Well, it is the set of all the nodes U such that the edge U comma V is in the edge set. So it's basically saying that the neighbors are basically neighbors of the vertex V are all the vertex U such that the U is one of the endpoints of an edge incident with the vertex V. Okay. Of course, if there is a self loop at the node V, then V also will be considered as its own neighbor. Okay. And once we have the definition of a neighbor of a single vertex, then the definition of a neighbor of a vertex set A is the following. So if A is a subset of A is a set of vertices, then the neighbor of the set of vertices in A is basically the union of the neighbors of all the individual vertices in the A. Okay. So for instance, if I have this bipartite graph, well, by the way, the neighbor and the neighbor of a set of vertices is defined with respect to any graph, but we will be using it in the context of bipartite graph when we will be discussing the Hall's-Marriage theorem. So if I consider this bipartite graph, and then if this is my set of vertices, then its neighbor set is A, C, D, and P. Why? Because the neighbor of the vertex requirement are C and D, and the neighbors of testing are B and A. So if I take their union, I get the set ACDB. Whereas if I take the subset architecture comma implementation, so the neighbor of architecture is only C, and neighbor of implementation is P. Okay. So what exactly is the necessary and sufficient condition given by the Hall's-Marriage theorem for complete matching? It states it is the following. It states the following. The Hall's-Marriage theorem formally is the Hall's-Marriage theorem statement is the following. If you are given a bipartite graph where V1 comma V2 is the bipartition, then uh, for complete matching from V1 to V2, you need the following necessary and sufficient condition. You need the following. You take any subset A of V1. That subset could be an empty subset, it could be a subset with just one vertex, or it could be the whole set V1. You take any subset A of V1, the number of neighbors of that subset A should be greater than equal to the number of nodes in the set A. Of course, the neighbors of the set A will be in the subset V2 because that is the definition of your bipartite graph. You can't have the neighbors of the subset A within the vertex set V1 itself. The neighbors of A will be in the other subset in your bipartition, namely V2. So what it says is you want to find out the complete matching from V1 to V2, right? If this is a bipartite graph, and if you have any subset A here, okay, it should have either the same number of neighbors in V2 as the number of nodes in A or more neighbors. Okay, it can't have less number of neighbors in V2, right? And that precisely was the source of problem due to which we don't have a complete matching in the graph of organization number 2, right? So if you take this graph, this was the graph for organization number 1, and in this graph we are able to find out a complete matching from the vertex set V1 to vertex set V2. This is because you take any subset of V1, you take either AB or you take BC or you take ABC, you take any subset, it has that subset has either the same number of neighbors as the number of nodes that in the subset that you are taking, or more number of neighbors in the other subset in your bipartition. But if you take this graph, graph G2, right, then this condition is violated, right? Specifically, the if you take your subset to be requirement, implementation, and testing, namely A is equal to 3, then the cardinality of its neighbor set is what? So requirements neighbor are x and z, implementation neighbors is only x, and testing neighbor is only x. So the number of neighbors altogether for your subset A that you have chosen here is 2. So you have 3 nodes to be covered or matched, namely requirement, implementation, and testing, but there are only 2 employees, namely x and z, who can handle those 3 modules. So the only way that you can ensure that all the 3 modules requirement, implementation, and testing are taken care is that you assign more than one job to employee X or Z, which goes against the definition of complete match. Okay, so we will prove this condition or the theorem, Hall's-Marriage theorem, in our next lecture. Um, I conclude today's lecture. These are the references used for today's lecture. To summarize, in this lecture, we introduced the notion of matching. We saw various types of matching, like maximal matching, maximum matching, and complete matching. And we saw the necessary and sufficient condition for the existence of a complete matching in a bipartite graph, namely the Hall's-Marriage theorem. Thank you.